Okay, well, thank you everyone for joining us again. I hope you had a great morning. I think there were some really great sessions, and I guess once again, we thank all the panelists and participants for joining us today. And we have another great session ahead of us. We have the expansion of simulation and engineering. This particular session is being moderated by Hein Schumet from Mauser Electronics. And we'll let Hein, you go ahead and take it away.
All right, welcome back, everybody. I hope your morning is going well so far. So before I ask the panelists to introduce themselves, I guess it goes without saying that hands-on is critical to our industry and our education process, whether it's hands-on mouse or hands-on oscilloscope, hands-on soldering iron. I guess increasingly it's hands-on mouse as the solutions become more and more complex, the tools have to become more and more complex, and simulation has become a robust part of our educational and our professional practice. So we're going to talk a little bit about that and how that's been evolving recently, both before and as a result of COVID. I know on the business side, the way that we communicate and the tools that we use at Mauser has been transformed by the pandemic, and in many ways it's been very, very positive. We are a global company, and I don't think we communicated particularly well globally, and we're able to cooperate as well globally as we are today because we were forced to all go home and relearn how to communicate with each other. And a lot of modern electronics design is collaborative, and I'm sure there's been some impact, and so we'll go through some of that. But before we do that, let's have the panelists introduce themselves, starting with Chad, please. Who are you and what do you do?
Thanks, Hein, I appreciate that. So my name is Chad Alley from the MathWorks. I am a customer success engineer. What that means is I partner with different universities around the US. I work on a team of other customer success engineers that support worldwide efforts with universities, and we partner with them to help bring computational thinking more inside the classroom and within researchers' reach through our products. So I've been in this role for about 2 years now, and previously to this, I've had some industry experience working with Boeing commercial airplanes for 7 years as a fuel systems engineer.
Excellent, thank you. Randall.
So Randall Resley, I recently was the Vice President of Applications Engineering at DigiKey Electronics. But for the last year and a half, I've been my own company, doing some consulting, helping companies figure out product development strategies, how to market those. But I'm an electrical engineer. I've got a master's also. Both of those are from the University of Cincinnati. And I went through school. So University of Cincinnati was, I think, the first cooperative education institution in the United States. So I went through that program. It was a 5-year program, 4 years of in class and 1 year on the job. And that was in the 70s. And I think that's given me a perspective of how things have changed. You know, when I went to school, the microprocessor was invented in my freshman year. And by the time we graduated, there was so much demand for people who could use these devices. So simulation and how we did things and how we're going to do things are some things I look forward to talking about.
Thank you. Rachel.
Hi, I'm Rachel Kimmerling. I'm the product marketing manager at Liquid Instruments. I focus on go-to-market strategy for our education line, and I have a personal passion, professional passion for augmenting student impact and accessibility through the different tools that we can make, and obviously maps really closely to what we'll be discussing today.
Thank you, Rachel. And Casey.
Yeah, my name is Casey Latham. I am the Pathway University Program Manager for Keysight. So I've been at Keysight for about 3 years, just about 3 years now. Prior to this role, I was a field engineer working with universities in the Texas area and the border states on both research and teaching things. So, and prior to that, I was at Baylor University, where I got my bachelor's and master's.
Excellent. So before we start talking about the last 2 years and everything that's gone on in the last 2 years, let's set the context a little bit. So I'd like to get folks to talk a little bit about simulation itself and its relationship to the profession and the education in the profession, and some of that evolution that was going on before we got to code. Randall, you want to start, and anybody else jump in when you're ready?
Sure. So as I was saying, in the history of my being in the industry, things have changed a lot. Yesterday, I think it was Alan Feinerman was saying that in order to solve some calculus equation, some differential equation, it was very easy to go and pull out some analog components and build that in the form of an analog computer, which I had a course in. But that isn't done so much anymore. People are getting to be less hands-on. But what you are able to do is instead in front of a computer and test your understanding of something, how something operates by simulating. And so this has become incredibly important. The challenge now is whether or not what you're simulating is reflective of the real world. And so whereas sitting in front of a computer running a simulation is one level of abstraction, what's happening today is that you're able to sit in front of a computer, which is actually connected to real hardware. And so simulation is getting a lot more mature. And I have more to say about that. But Chad, I'm going to turn the floor over to you.
Oh, thanks for that, Randall. I definitely agree with a lot of the points you raised. I come from a different or a similar school of thought, but also from a different perspective in the sense that during my time in undergrad, I went through and I didn't actually experience learning anything about simulation. But when I got to my first job, which was Boeing, it was, do you know how to do this, right? Because at that point, there's a gap between academia and industry where they're trying to find out, well, hey, I'm hiring you as an engineer because I want you to bring value to my company. That's why you've been hired. That's why you've been brought onto the team. And a lot of what they're doing costs millions of dollars, right? I mean, these are companies that are for profit, and any kind of loss is going to be detrimental to them. So they want to figure out the best ways in which they can help save some of that cost. And part of that is through simulation, which is a big part of my role when I was at Boeing, was making sure that we would be able to design our fuel systems, understand them from the beginning all the way through, including all the controls and things like that, before we ever go out to a fuel dock, before we ever fly it in the actual airplane, before pilots ever see it, just to make sure that it's doing what it's supposed to do at all times. So, I think when it comes to the importance, I know we talk a lot about hands-on and things like that, and I agree. I think that's still going to be paramount for engineers that are coming out into the field to be able to be familiar and face-to-face with a product. However, I think that with the augmenting of simulation in academia, which is something that I wish I had at the time, it would have helped me better understand and appreciate these different systems. And not only that, be able to dig deeper, discover, and really start asking more questions, which is something that we want students to do more of, is ask more questions and be curious about these systems and things like that, so that we can expand their vision, so that by the time they get to industry, the gap in knowledge or the gap in perspective isn't as wide as something like the Grand Canyon, right? Which was my experience.
One other thing to add on, I was at an ACETA conference probably 7 years ago, and there was a panel discussion. This was a live discussion, and on the panel was a vice president at Texas Instruments, a vice president at Analog Devices, these very large companies. And one of the questions from the floor was, should we as university be providing more hands-on? And what the panelists universally said was that, no, you provide the theory, we will complete the education with the practical hands-on. But I think there are changes taking place. I think this level of simulation is done at a more personal level today. I don't think you need some expert at a company to tell you how something works. So I think that things are changing for the better, in that you can still get the theory at school, but with some of these online tools and some of the hardware that you can easily buy, you can teach yourself a lot of that hands-on. The other thing too is so many people, as we've seen in earlier presentations, presentations, these guys are getting out of school and right away starting a company. And it used to be when I graduated, very few people would start a company. Instead, you went to work for a company, and those masters around you, they would teach you the ropes. But that's much less so the case today.
Right. I think that Chad's experience that he just spoke to about industries wanting ready engineers on day one to be able to jump right in, that, that and what you're also saying, Randall, really maps to this hybrid solution that I think we're going to look at moving forward. Yes, we need people to have more training in simulation because those are tools that people use in the industry. And then, yes, we also need to make sure that people can jump right in and be comfortable on the hardware side as well. And, I think that this in many ways was brought on or exacerbated at least by the pandemic. And now we just have more tools that are at the disposal for the students moving forward. Remote tools, portable hardware solutions, simulation capabilities, that's only to the benefit of the student as far as access goes and setting them up for future success. I caught the tail end of the student panel earlier, and one of the students had commented that he had wished there had been more early exposure access to the ability to tinker early on. And I think now that more students have those capabilities because of these expanded tool sets that were made available to them during the pandemic.
Yeah, I do want to add on one more thing that kind of bounces off what Rachel and I think everyone actually had hinted on. So one thing that I really like about working at Keysight is we get to, in my current role, I get to look into all these different industries, whether it's 5G or quantum or like high-speed digital. And one thing that's pretty much across the board is, designs are becoming, they're becoming smaller and smaller and smaller. And the smallest change, whether it's in what component you select or maybe like soldering or a trace width or something, but the smallest change can have a big impact. So a lot of companies are trying to determine exactly what they want to simulate from day one, so that before they even go out to get their first fabricated device, they have a pretty good idea of how it will work. And so understanding this design flow is something that the industry has sort of really worked on and sort of integrated over the last several years. And I think it's something that students are going to want to, they don't have to, be masters of, simulation or of hands-on troubleshooting, but they need to have a good idea of the design flow so that they can at least conceptualize it and think of, okay, I'm starting a design. What are the other processes that are going to come later down the line? What are the implications for the decisions that we make, right now?
Yeah, and that's great, Casey. And just to add on to what Casey just said as well, and I think we'll dig into it a little bit deeper later, is something that companies need that they may not be necessarily aware of, or they might be, on the tail end trying to catch up with current industry standards, is something like systems engineering, something that students don't get enough exposure to when we're talking about looking at things from a holistic standpoint, looking at problems from a holistic standpoint, right? Understanding what the problem you're trying to solve is and why you're trying to solve it. And through the advent of simulation, you have the capability of looking at larger systems in a virtually non-risk environment where you can see how all the different systems interact with one another, giving students that exposure and perspective of what it means to work in a larger system and not just in a silo. And so when they come into industry, they have that perspective, because typically you're going to be working on an integrated product team or an IPT, right? And you're going to be dealing with one piece of the puzzle that goes in, that's going to fit into the overall scheme. And you have to understand how your other team members or non-team members that are contributing to that project and how what you're working affect what they're doing and vice versa. So even with simulation, it can even provide those kinds of perspectives early on, and really, like Rachel was mentioning, allow students to tinker and really experiment and see, like, okay, if I do this, what happens here, without having to deal with necessarily any real risk, but see what problems could come, and again, increase the curiosity and experience of that specific individual.
From the perspective of, go ahead, Rachel.
Oh, go ahead. Oh, thank you. Yeah, and I think one thing, and I know it was mentioned early on as Hayne opened the panel, but one thing that I have found really encouraging about this discussion and others that arose as we sought to provide students with more tools while they were at home, is that you've seen the fall of a one size fits all solution, right? It's not people that are just advocating for one way of doing things, but how simulation can augment one learning approach, or how hardware fits into that in a remote environment. And the more ways in which we can help students understand how these different tools fit into a broader learning perspective, the more we can undermine that siloing effect more quickly.
I just wanted to quickly mention, there are online resources that help somebody appreciate what is the design flow. One of them is on maker.io, where a startup roadmap. Here's what you do in the first step. Here's what you do in the second step. So some of that content is out there. But again, if you wouldn't know to look for it, you have to be directed to it practically.
I was going to say, from the perspective of distribution, just a story that reflects what people are able to do for themselves these days, these really complex systems. This is years ago, long before COVID. Mouser was picking up either Xilinx or Altera. I don't remember which one it was, but that's a complex product. And we had trouble convincing the company that Mouser would be able to sell it. Because we don't have field application engineers. We pick up 1,000 new customers every day. So we do not expose high-level engineers to help you build anything. And the supplier was worried that we wouldn't be able to sell the product. And of course, it flew off the shelves as soon as it was stocked, because people were already designing with those products without ever having talked to anybody and without ever asking for any help from anyone, because they were able to use tools like these to be able to get that done. Certainly different from the way it was even 10 years ago. So let's move on to the new world and everything that happened to us in the last year and a half. And as I mentioned, a lot of the tools, at least in my job in the corporate world, got shuffled, and new capabilities were introduced that really changed the work that we do. Has that happened in this part of our industry? When it comes to simulation and how people are working in industry, has that changed to any great length, and does that change any gap potentially with academia? Are there things that you can make folks aware of that they should be considering when they are looking at simulation in the classroom? Anyone want to jump in?
Well, I think, Hayne, you kind of nailed it early on in the panel when you talked about how your global communication across Mouser had improved over the course of the pandemic. And I think that, in a lot of ways, at LI, our R&D team is in Australia, for example. And so there's a lot of communication that goes on across continents, and you need to be able to share information and share knowledge and be able to present or collaborate on projects in a remote fashion. And I think that the universities in a lot of ways focused on more individualized projects. And so how, they kind of adapt to that group collaboration in a hybrid environment moving forward, I think is going to be one of the essential components to, what students are going to experience as they leave the education system and move into industry.
Yeah, and I think also to bounce off what Rachel has said, if we think of, what was it, middle of March last year, March Madness was canceled, and then the next week students had spring break, and then universities were expected to come back, that next Monday and have a whole plan for the rest of the curriculum for the whole semester. Well, actually, maybe for just 2 weeks, but it ended up being for the whole semester. And so they, pivoted really quickly to trying to get away from the lab, doing simulation, because that was more of a stopgap measure. But then in the fall, I think what we started to see was more of a measured approach, where you had simulation that supplemented what they were learning in some sort of hands-on lab, whether that was, remotely accessing their physical lab, actually coming into the physical lab and just, having a reduced capacity, or whether it was, taking home, like the oscilloscope or something. But yeah, so I think, what we realized in the course of the spring is that, you can't do simulation all on its own, but as we sort of figured out how that worked and, the challenges or the pros and cons of it, we came back in the fall with a much more balanced approach that I think benefited both, students and, the universities.
And I think on the industry side, we also felt this, we took a different approach in how we made sure that universities knew that the tools that we had created for them were available. So I think about supplemental coursework, ways to engage students, especially on the hardware side, right? Like how students could access hardware remotely before we got quite as nimble as we became in the year that followed. So I think that was another big step for us, not just in the reshaping of the roles of professors, but on the industry side, making sure that people were not just aware of the products that we have, but just the tools that were available to ensure that there weren't gaps in learning during those first couple of weeks that were such a scramble.
And Rachel, you mentioned the hybrid approach. Can you define that a little bit better for us? What do you believe that means and the virtues of it?
Sure. So I think moving forward, when we think about a hybrid approach, it's not just going back into a university lab at fixed lab times to utilize fixed function equipment. It means that, we have more portable hardware that's accessible to students, more software and simulation approaches that they can use at home so they can independently work on projects. It's not simply limited to what you can do when you're in person on a campus. And I think that just has broader implications for remote classrooms, online learning, and how we can make sure that learning specifically is more accessible for more people, even if that's from a geographical perspective or from just a general accessibility perspective.
That's great. Anyone else want to talk about that?
Yeah, there is a technology that you can have in front of you. It's real hardware that you can buy, overnight shipment type stuff, and small little boards that have a single function on them. So you can aggregate those into a system and then have access to it. But what's really fantastic today is that you can have remote access to it. So whether the hardware is with you or on the other side of the world, there's this thing called Planet Debug that allows you access to it. Now, with some of the collaboration that's been mentioned, I'm not sure that we've solved the problem of having multiple people access that same hardware simultaneously. But certainly at a personal level, the technology exists that you really can be on campus or not on campus and be doing hardware and debug and simulation.
Yeah, what Randall was saying, we've had some good experiences with other universities where, they already made an investment in the hardware. So, how do they take advantage of the hardware that they have? Because not everyone can take home, a 50-pound vector network analyzer. So we've seen some success with, remotely accessing the equipment, and then, just getting a group together to remotely access the equipment. Only one person can, can click the mouse at a time, but you can sort of, essentially just share the mouse virtually between everyone, where one person's controlling it at a time, and you guys are all collaborating to say, hey, actually, no, that functions somewhere else, or hey, let's try this approach to figure out how we can get this data.
Yeah,
we've seen that work as well.
Yeah, I think that's a good point, Casey. And I think what everyone can really agree on is that there was not a one-size-fits-all solution for every school, right? As you said, some schools already have solutions in place, and remote accessing with shared hardware was the best solution for them. But I also think that there is a strong significance to making sure that every student has the opportunity to tinker individually and become comfortable with the tools that they're using. And one thing that I think can get lost in even the kind of in-person lab partner structure, if one person is primarily interacting with the hardware and as another looks on and takes down the data and they both write a lab report, but is the student that looks on as prepared as the one that's actually handling the equipment? And we need to make right, exactly. And so we need to make sure that there are tools available on both sides to ensure that the answer is yes. And that is really, I think, where that marriage between hardware and simulation can be helpful. And as our tools in simulation map well to the hardware that people will actually use, which is, I think, why this communication between industry partners is so significant in that area as well.
Interesting. I'm curious. I mean, it seems like almost anything that you can do on the bench, you can simulate. We didn't talk about this in our preparation for this meeting, but is there an area where simulation still falls down? What is the most difficult thing to simulate and to do without actually touching at this point?
Yeah, so I think kind of what Rachel was saying was, one, I think tinkering, that's kind of difficult to do in simulation. You can do sort of a virtual tinkering, but, I come from an RF background, and there's, probably, 70% of issues in an RF environment are either your cable or your connector, which you can't really, you can't do in a simulated environment. And so being in front of a VNA and sitting there and being like, okay, why is the data that I'm seeing not lining up with what I'm expecting? And then, trying to, readjust your cables, or, oh, my cable was bad, or, oh, well, I need to use a torque wrench to fully screw it on. I think that's what comes to mind when I think of the big limitations of simulation, because simulation is assuming that you have a good connection.
A good connection and a good model. So many times you'll end up modeling something that you thought is what the real world was, but in reality, your understanding of what is really the truth of the matter isn't right. And so, I don't see a way out of not going that step of testing on hardware also. Simulation is a means of catching your early defined errors so you can fix them when they're cheaper to fix, but then going to a platform that allows you to see whether or not your understanding of the world was actually true. I've seen that more times where there's a rude awakening too late in the design phase.
Yep, absolutely. Yeah, and I've seen that firsthand in my previous life. So, and Randall, you raised a really great point. I even during my time, I believe that one of the adages that always floated around as we did simulation was that every model is wrong, but some are valuable, right? And that's very true, because you can try and simulate the real world as much as you want, but there's always going to be some little thing that you might not be able to get exactly 100% right? But at least you can infer and get a better understanding that you're pretty close to something. And you know that when you actually build it in the real world, or you test in the real world, you have a much higher chance of success, right? Which means you're going to end up spending less time and less money down the line when you're actually going to finish testing and integrating this actual product. So yeah, simulation, we can say it has its limitations, but I mean, it is what it's to be used for, right? It's not going to completely replace things in the real world, but it's going to help us get to a much better answer a lot sooner with lower cost.
Now, Chad, you said you worked for Boeing. I don't want to dig too deeply, but what time frame was that? Yeah, that was a simulation problem, right? I mean, that fault wasn't foreseen, and it's a shame that it wasn't that sophisticated that could have been discovered.
You're talking about the 737 MAX?
Yes. Yeah. I mean, to be fair, it was foreseen. There's a lot of systematic issues involved in that, right? It's not just from the engineer perspective, but also from a corporate system perspective, right? All the way up and down the chain and how things work. So, we have to look at it from the entire picture, right? Not just who designed the software, how the software was tested, and how and the communication that happened in between it, right? There's a whole lot more in terms of soft skills and stuff like that, in terms of being able to express different opinions, ideas, and understanding the way in which things work. But yeah, we can't just only fault it to the software. True, the software is what drove the ultimate issue, but right, systematically you have to look back and go, and as all engineers do, right, go back to root cause.
Yeah, but you bring up an excellent point, and that is the human factors of it. I don't think anybody is being taught how to bring up a disquieting finding in a simulation to the manager. You know, I'm thinking of that building inspector in Seashore, Florida right now, saying, "Hey, I found this, but what's anybody going to do about it?" That's
right. Or who should I tell about it, right? I mean, this is, I mean, one of the big things, I think even someone mentioned in the chat, right, the human factors, but ethics by far is one of the things that I've seen is lacking in academia that we really need to make sure that we stay on top of, right?
Beautiful.
And
right?
on top of that, I think simulation is, to tie that back into simulation, it's great that it allows students to go beyond and go see things, but it also, in a sense, removes the veil of what actual risk is, right? You know, I've done talks at different schools in my role to freshman engineers, and I've actually used, unfortunately, the example from Boeing, but it's very pertinent, right?
Sure.
Because I'm making sure you understand that you're going down this route. Yes, engineering is fun, engineering is great, but there are many risks involved that you have to take into account. And through simulation is how we to reduce risk and hopefully have far less of these kinds of issues, right? Focus enough on the perspective of engineers as we're building stuff for the benefit of society, not just to build it just because we can do it.
That's right.
I think that's a really good point. Oh, go ahead, Randall.
I was just going to say, becoming a professional engineer, you have to sign an ethics statement, which basically is a recognition that you are a public servant. Ultimately, you know, people's lives depend on what you engineer. And coming back to the topic of simulation, it is the simulation that really provides somebody the first opportunity to highlight a liability in a design. And the other thing that's nice about simulation is you may not have access to the node in a real hardware design. With surface mount, with ball grid array devices, it's incredibly difficult to simulate, so or to find in hardware. But with simulation, with enough probing, you can actually touch those. And I want to real quickly mention, I'm going to give it the floor. Hein, there are a whole lot of chat topics that you might want to go through and form questions from. I'll let you be the arbiter to those.
Well, I think we've got about 10 more minutes of topics that we agreed we'd talk about. And then I think we're just going to open it up to the floor and we'll dig through the chat when we get there. And unless anyone feels like raising their hand and interrupting the conversation, if you've got something to say that's directly pertinent to the recent discussion, we can go through that. And of course, Sid, what you got?
Hi, everyone. I heard lab mentioned so many times, you know, it feels good right here. What I think has happened in pandemic that we weren't ready to do is we had to use simulation. And we used to use it before, but it appears that students liked simulation of a protoboard on Tinkercad, and then they would use the breadboard to actually wire. And they could write a code on Tinkercad for Arduino, and they would actually use Arduino to do it. So I think for the longest time, the theory folks have been saying simulation is your gateway to, you know, PhD or theory or higher education. And I think students need to be convinced that that's true. We haven't found a way to, in the labs, turn the lab into a data gathering system. Once we create that mindset that all the information that's being collected is a data, can be processed, I think the journey from simulation to hardware will become easier because we don't post-process the data after the lab, right? Once you do frequency response of a circuit or a second order amplifier, we just leave it as a circuit. We don't actually go into wavepoints and say, find from the graph the response, right? And I think that we need to make that transition so that students feel great about simulation. And so from your customer perspective, you know, I need to find ways to have engagement with students, become better with simulation tools. And unless we do that, I think it's hard to implement simulation as a first step before students feel comfortable with technology. So computer science is a great example, right? They work in the environment. They're always simulating and problem solving, and everybody wants to do computer science. So there must be some gratification from those tools that works. And I think we can learn from there. Anyway, thank you so much. Great panel, great discussion. Appreciate it.
Talking about large real world simulation. My wife recently got a Tesla, and watching that car try to figure out what's a dog and what's a human and what's a pickup truck, and the fact that Tesla is gathering all of that data in order to make their simulations better, because basically they have to simulate the world if they're going to keep the car in the lane and not run over anybody. It has to be the largest experiment in simulation that I can think of. All right, if no other immediate questions, let's talk about collaboration a little bit. At Mouser, the Mouser website that I'm responsible for is built by teams of engineers. It's a Scrum team. It's 2 developers and a QA person and a product owner and a designer. And before we got to COVID, we had argument about whether or not all these people have to sit immediately next to each other in order for that Scrum team to be fully productive. And we had to rearrange cubes in order to get them into their pod so that they could be productive. And then we threw that basically all out of the window because everybody moved home, and we had to learn how to do all of this virtual. And now we're having to learn how to do it halfway virtual, because 4 people are in the office and 1's in India and 1 is at home. So in the engineering process, in electronics engineering, is there a corollary to that? Has that work changed? Have the tools of collaboration changed? We also discussed a little bit about Google Docs and the fact that 5 different people can be writing 1 letter at the same time. I don't think that's there yet in engineering, and maybe shouldn't be. Anyone want to comment on that?
Yeah, I can start off. I'd say probably by design, in a sense. Maybe there are people working on it. And they might want to go that route one day. But in certain cases, I could see for very large integrated products, 5 people work on the same, code or even simulation model and things like that, with things changing dynamically all at once, can lead to far more errors than one would want, right? I think one of the benefits that we've seen even pre-COVID, and I guess more exacerbated after COVID, is the use of shared repositories, right? A lot of GitHub, SVN, things like that, in which you can actually commit your files to a shared repository that everyone can access. You can pull those files, make modifications, send them right back, and then people can see all the changes that have been made, so they know not to either overwrite what you've been doing or change anything that might affect the overall final answer or things like that. So they have ways, and then also conflict resolution, especially in these kinds of systems, which is great, where 2 people commit the same model and they get a conflict to say, well, which one do you want, right? So that allows for more team collaboration to make sure, okay, hey, what exactly do we want to have moving forward? And that's a collective stance that has to be taken. So definitely there is avenues in which that help with the collaboration. But as far as, people doing all the same work at the same time on, code or simulations like they would do in Google Docs, I'd say, from an engineering standpoint, that could lead to far more issues than we might be aware of at the moment. And probably by design is why we haven't seen it pop out as much as of yet.
Yeah, I think one thing that we were talking about in our pre-meeting was, if you're designing an amplifier and you 2 people are drawing 1 wire at the same time, and then someone deletes it and then someone tries to re-add it, or you wire it up incorrectly, that would be a big issue that you would have to solve. So I think there's several different ways that you can collaborate. One is the Google Docs version, where it's live editing, and then another is what Chad was saying about where you have shared repositories. Everyone has sort of their own responsibility. Like, you are responsible for the first stage amplifier. Here's what you need coming in, and what you have going out, and then what happens in between those is what you're responsible for. And then I think also the importance of, documentation, being clear with what you're doing in there and trying to make it easy so that, say you're out on FTO. I know last week I was the only one in the office. I'm pretty sure like 9 out of 10 people that I normally work with were on FTO. So, there's times where that's going to happen, that you have to leave your work in such a way that someone else can look at it, know what you're doing. And if, a change needs to be made while you're unavailable, then that's something that they can work into the design.
I think there's a key here, and I think the world has changed a little bit for the worse, but just to point to our history, the fact is electrical engineers have always been collaborative, and they've done that by making electrical circuits that have well-defined interfaces. So back in the 70s, when electrical engineering did not have much software in it, we went ahead and designed packages with limited number of pins, and the functionality of those pins was carefully chosen so that they could be configured in the most alternative ways. And then compositing all of those chosen chips on a board, that's a masterful collaboration. The challenge with going more and more software, I think, is the challenge that there isn't limitation. I've got an infinite amount of memory. I've got a practically infinite amount of CPU. And so I think the real key to the future is getting software better modularized the way we used to. And then collaborative online tools will allow us to simulate what each of us did by virtue of making calls to that interface. And I just want to cite a famous paper. It's among the top 10 papers in all of computer engineering, and it is called "On the Criterion to be Used in Decomposing Systems into Modules." And I don't think that's taught so much, because there's also a current book called Writing Software. Now, this writing is spelled as in correcting software. And what that guy mentions is that paper on the criterion of decomposing systems into modules. The thing about that paper written by David Parnas from Carnegie Mellon was that it was written in the 70s. So this was a known problem, the software, early on, but because of the expansion of memory and computer systems, we've gotten sloppy in our implementation of modularization. But if we get back to that, I think collaboration of online will serve us well.
I know we've definitely seen the code library explosion on our side, and there are, at least on the strictly software side, there seem to be some really good tools out there now that are able to monitor use and say, okay, you're using this code library that you borrowed, and you're using 5% of it. Do you really need all of it, or can you cut some of the weight out? So before we get to the questions in the chat, real quick. Looking forward to the future and to what's going on in simulation. Those of you that are tied into this, our panelists, are there things that are on the horizon that are coming out, new feature functionality, capability, that are going to change things that academia would like to know about? You guys have been great about not advertising for your companies. We appreciate that, but it's also really good to hear about what your companies are working on and how that may affect us in the future.
So I've mentioned before, this ability to either buy the hardware in forms of little what are known as clipboards and plug those together in front of you is one thing, but you can also access that hardware through this thing called Planet Debug that people should know about. So rather than actually getting the hardware delivered, what you do is you buy a reservation for the hardware. In your application, you request what boards you want, and there can be a myriad of those boards. There are well over 1,000 boards to choose from, and then you get access to that hardware remotely. And I don't think that capability is well known. It's pretty new, all in all. That's called Planet Debug, from a company called Microelectronica, and it's micro because they're in Serbia. We would say Microelectronica.
Anyone else on the future of simulation?
And Chad, you can probably make some comments on MATLAB, with its ability to go from a mathematical simulated environment to actual hardware. I mean, that's might be well known, but are there advances there that you can speak to?
Yeah, absolutely. I was just about to touch on that actually. So I think one of the things, from a simulation standpoint, model-based design is something that definitely is something that we want to continuously help grow, especially in academia, so that that idea and that philosophy flow into industry. But I think one of the bigger things out of that is what's been known as digital twins. That seems to be an up and coming thing that, especially in industry, is wanting to be very familiar with. And basically, the idea there is you develop a simulation model of your actual system, and you use a combination of AI like machine learning and take data from the field, actual test data from your actual product to continuously improve your current system, and then possibly even iterate on future new designs. So you have those capabilities along with also taking the systems that you help improve and generating code directly from those onto hardware itself. So, these are things that are definitely coming and somewhat already in the works as well for those that might be familiar with or those that are interested in it. But I think this is a great opportunity to not only expose more students to what the idea is behind simulation and how important it can be, especially to their futures and what their employers are going to be interested in, but also allowing them to continuously innovate and think about different things as well.
Yeah, and so one thing that we're working on is just doing more with simulation, seeing how you can avoid delaying your go-to-market because you had a bad fab, or not a bad fab, but a bad design. So how can we improve the designs? How can we get the simulation models to be more accurate? Can we take into account like different electromagnetic effects, ground loops, things like that? And so that's something that we're putting a lot of emphasis on specifically for industry, but also I think that does have a big impact on academia, because if you can, with the touch of selecting a few different options, figure out that what's causing your issue is a ground loop effect on your circuit, which might be kind of difficult to measure, that could help explain different types of theory and can help in your troubleshooting game as well.
And I guess I'd like to add one more thing that I think is really important. Again, something that I learned in industry versus in academia, which I think is a detriment to me and possibly to other future students, is the ability to write and understand requirements, right? Requirements for design, requirements for test, and so on and so forth. And part of some of the packages that we've been developing include those abilities to tie requirements directly to your simulation model and show ways in which you either you can run a simulation of batch tests to make sure you can either verify that that the requirements have been met or that they've been failed under different test conditions and criteria, to really integrate that idea and perspective of a real design perspective, like from V and V basically, and following that V all the way from your initial design concept all the way to your test and delivery and validation for the customer. So these are areas in which we're trying to continuously expand on, and hopefully, these are already something in the industry that they want to use, but it's a little too late, in my opinion, if we're not teaching students this and getting them ready for this prior to senior design or capstone, getting them involved in what it means to write a good requirement or understand why requirements are so important. And Randall, to your point, a poor defined set of requirements is part of that 7 through 7 max issue. So.
And I think I just want to, I just wanted to add from our side. So we sit definitely more in the software defined hardware setting. And, a lot of you know from previous ACETA meetings that we did launch a portable test and measurement device that's aimed at students. And one of the things that we're looking at over the next couple of months is adding additional instruments to that tool set to expand use cases across curriculum. And then even beyond that, as they move into their professional lives or, their future as makers and tinkers for, their lifelong approaches to learning. But one other thing that we're constantly focused on is making sure that the, relationship between the software that we develop for students to be able to use and the hardware that they're interacting with map really intuitively. so that when they enter into the industry, it's not that they've just been trained on how the oscilloscope on our hardware platform works, but how an oscilloscope would work generally speaking, right? So they're not learning how to use the hardware, they're learning the fundamental concepts, and that's enabled through the software, that we develop to accompany it. So that's always a big focus for us, and just ensuring that we're continuing to map to that as we develop future tools.
Sounds good. All right, we've got 10 minutes. Let's move to question and answer. If anyone has a question, please raise your hand and we'll call on you. Otherwise, panelists, if you will dig through the chat and see if there's something that you wish to comment on, that would be helpful. I'll start off with a fairly specific question from Patrick at Infineon. Is it possible to reliably simulate a mixed signal system, i.e. analog and digital plus and MCU? Does anybody know?
Reliably is the key word there. I mean, that is, those can be incredibly detailed and overly complex models that can be very slow. I mean, to do if that MCU is in a piece of programmable logic, it can be hours and hours of compilation time. So, so what we do is we simplify those things to make them quicker, but now are they reliable? So I think it's largely problematic that you can't know really how reliable it is. When you manufacture an integrated circuit, there's something called a fault grade. A fault grade is used to determine how much of the chip have you actually tested, how many of the nodes have you actually toggled, and that's something like over 95% is a reasonable fault grade for an integrated circuit. I'm unaware of any kind of fault grade for a simulator.
Well, that's why I asked, because with our PSOC product, which has digital, analog, and an MCU all in one chip, we've never been able to, simulate it fully. You can test the code running in the MCU. You can test the digital logic, but then the analog is always the one that's most difficult. So, just was wondering if something has come out in the interim that I missed that could simulate all this at once.
I think the solution to that actually is hardware in the loop. So you're not simulating with a model, you're simulating with the actual devices that are driving signals to one another. But then, of course, the thing generating the model, that is the real world. How accurate is it? That's
well, yeah, and you're disturbing the circuit by the fact that you're simulating it.
Yep.
All right, I'd like to recognize my worthy competitor, YC.
Thank you very much, Hayne. So I just want to go back a little bit to an earlier point in the discussion about whether human interaction is important in education. I think it is extremely important here. I mean, even the process of students sharing notes with each other or doing study groups, that builds team building at a very, very fundamental level. And I think that the ability to do hands-on labs is something that will have to continue despite everything that's happened around the world so far. But also, on the other hand, doing remote labs, I think to a certain extent, where you have the scalability of the interfaces or the hardware, I think that's also useful to a certain extent, where perhaps there's a situation where the instructor needs to have students test out something or play with something to augment an understanding of a later discussion in class. I think that ability is invaluable there. So there's definitely a balance between in-person learning and in-person interactions between students and virtual interactions. I shudder to think of all the students who are forming teams right now, albeit remotely, and they've never met each other, and they're all over the country, and essentially that's just a remote working group. And we all know how effective these groups are, even from our corporate experiences. So I would definitely like to encourage universities to adopt a balanced approach to this. It's not all simulation and remoteness. It's not all hands-on and hardware. There can actually be be a very useful hybrid scenario to develop here. That's all I want to say.
Yeah,
Yeah, couldn't agree
I
more.
completely agree. We talked to a lot of universities early on in the pandemic, and that was one of the biggest struggles from these students is that they were isolated. Rachel said earlier just how much they relied on those individualized projects, and I think setting up like a standing team meeting where anyone can just come and ask questions, or it's kind of like sitting in the lab together, because I think there's a lot of to be gained where you're all just working. You're not actually like talking or engaging with each other, but you're all just working on something at your but you're online with each other where you can ask them questions. So I think that's a big thing that we learned, at least on the corporate and side in terms of COVID. So yeah.
Yeah, just to add to that, Casey, when myself and one of my colleagues went to a virtual reverse career fair to speak with internship candidates this year, they all had presented these projects that they had done through IEEE, and some of them had done group projects, some of them had done individual projects, and that individual sense of like seeking out those areas to collaborate with other students or design and implement their own project was incredibly impressive, just in a general sense. And I think that just speaks to the fact that students are so capable, and as long as we provide them with the additional tools to their success, there's really not limits to what they can do. But at the same time, I think that YC's point is really excellent, that there should be more of that encouragement of both approaches, from the more pedagogical classroom lab approaches to doing things in a future hybrid environment.
Needed to unmute myself. Going through the chat, there's a lot of comment more than question. Is there anyone else that's willing to put forth their comment in the form of a question so that we can get a little bit more interaction before the end? We've only got like 3 minutes left, so. Or any last comments from the panelists?
I think Aisha was making some excellent comments there.
Yeah, guys, I think from being in the corporate world and then also being part of education, I think you need to have theory, simulation, and hands-on all integrated, because, as engineers, when we're trying to solve a problem, it's not all simulation, it's not all hands-on, it's also analysis of what could be the problem, right? That makes a good engineer. So I would emphasize on that. And I think whatever is a measurement tool, whether it's simulation or test measurement, I think you still have to create a problem-solving environment, an environment that encourages people to learn more, get curious. I think that's how you get successful in whatever you try to do in your future career or jobs.
I think that's a great note for us to finish up on. And I don't think we intended to say that simulation was more important than the other elements that you're talking about, Aisha. That's what we were focusing on today, and the changes in simulation today.
All of it is important. And I think there's so much advancement also in all these areas that we should utilize these.
Agreed. Any final comments, or should we move on?
Hey, Hayne, I'd like to ask a quick question. I don't know if this is a quick question or not, but there were quite a few comments in the chat about Chad's comments on sort of like, testing and validation and that kind of thing. And something that I've seen quite a bit in capstone projects is students don't often learn what the process is for designing and troubleshooting and what standards mean and that kind of thing. I wanted to see if there are people in the academic audience here who include that as part of their curriculum. We talk about experiential learning as being an ABET accredited, necessity, but we don't often talk about how to test something and how to define a test plan, which is pretty important for a lot of these, design projects.
That we should, but we don't. I call it the design cycle. And yeah, it's pretty much vacant from the program, except for capstone.
So I guess that's one thing that's missing in simulation today is the funny smell and look of that smoke, right? I mentioned I'm a hobbyist. I'm not a particularly good one. And I know all about that funny smoke. And so does my wife. She comments on it when I do something really, really wrong. And so far, I don't think any of the tools represented here have managed to pull that one off. Maybe
in
next
different
time.
ways, not physical smoke, but different ways. Some kind of notification.
It's the new quality offering.
Is it possible to do something in one of these tools and just have the whole screen go like this with, simulated flame or anything like that?
You could get creative. It's possible, but how much time do you want to invest in doing that?
There's probably an Easter egg somewhere where if you drive the voltage far enough, then you get the sound effect that just goes.
There's a couple of those built in for sure.
All right, thank you everyone panel, and thanks also Chad and Judy for helping organize this discussion. Really appreciate it. And I think we're turning it back over to Kim. All right, Kim, do you have any last minute announcements, or should I just close this thing up so we can all go eat?
Let's do that.
All right. I won't take very much of your time at all. Thank you so much for spending so much of your holiday summer time with us on Zoom for the last couple of days. I think the conversations were really good. I hope you found it helpful. I do want to thank everybody from ACETA, Megan, Kim, Sydney, and John, who did great work in getting this together, made it look easy. And also our organizers, our panelists, and our students. It couldn't have been done without everybody picking up the weight and getting all this stuff out there. The only other thing to discuss is getting back together again in New Orleans, which, there's some really attractive things about that. Part of that will actually be seeing everyone in person. I'm really looking forward to that. But then again, it is also just New Orleans, which means instead of cupcakes, virtual cupcakes at the breakout sessions, there might be miniature muffaletta sandwiches and beignets and things like that. And thinking about New Orleans is just making me kind of Zoom sad at the moment. So thank you for sitting through this and helping us get through the pandemic and back to business as usual. Really looking forward to seeing all of you in person and maybe even raising a glass when we get there. Good luck, everybody, finishing this out, and I hope to see you soon. Thank you again.
Thank you, everybody.
Thank you all.
All right, thanks all.
Bye-bye.